Niklas Beisert, and he's going to give us his second lecture on integrability and AdS CFT.
Okay, so before I really start, I could answer some questions that came to me after the lecture, or things that I also noticed. So one question was about references. Where do you find references? I don't have a good answer to this, but at least there's this this old paper by Zürich, brothers in Annals of Physics, some number, I guess sometimes in the 80s. This is about, don't know the title, but about SON model. Do you know the title?
I don't know if it's the same paper I'm thinking of.
So where they construct, I'm not sure, the S-matrix.
Factorize the elastic scattering is in the title.
Yeah.
It's around 1979, I think.
79 could be.
Well, I'm not sure.
Okay, factorized. Probably highly cited. Should uniquely identify it. Well, this probably explains in a similar but slightly different context of SON, the construction of a scattering matrix and related aspects. Okay, well, concerning integrability, there's also a review by or a lecture series by Fadeev. I think it might be 93. I don't know how algebraic beta ansatz. But probably Kostya has told you about that. Okay. So the other question that came up was why do we consider this loop algebra? Well, the answer is essentially because it's the symmetry of the S-matrix that we constructed yesterday. So it's not completely obvious at this stage, but well, it's actually not really the symmetry, but it's related to the symmetry. So it's the symmetry of the S-matrix, or almost. It explains the particle momentum in terms of representation theory. So we have an algebraic handle on the particle momentum and not only the particle flavor. And finally, it essentially gives you a way to find or construct solutions of the Young-Baxter equation. Well, why is that? Can be understood. So if you have this Young-Baxter equation, well, all of these are matrices, so this is a big combinatorial problem on the one hand, and on the other hand, it's a nonlinear equation. But in this loop algebra, as I told you, tensor products of representations are often, in some sense, irreducible. So in particular, if you have threefold tensor product that you need for these three particles that interact here, then this is a threefold tensor product. And in some sense, because this is irreducible, it already solves most of the structure of this Yang-Baxter equation. So just a heuristic argument why the loop algebra is useful, essentially because tensor products are irreducible, and this solves most of the combinatorial problem in here. Okay, so in this lecture, I want to essentially emphasize this third point and construct the Yang-Baxter equation, construct the solution of the Yang-Baxter equation, that is, construct the R matrix that we constructed by other means yesterday. But at first I have to admit that the loop algebra is not a proper symmetry of the R matrix. It's almost a symmetry, but the right statement is the R or the S matrix has Yangian symmetry. That is a deformation of the loop algebra. So that means when you have this product JA and JBN, this equals the usual thing, J Cn plus n plus some deformation, and I'm not really going to write down what this deformation is. I'm not sure if it's written down anywhere. Typically it's a big mess. But the good thing is for the things we will be considering, namely for these evaluation representation, this deformation does not play a role. So this deformation will be effectively 0 for us.
Is this a central extension of the algebra, the deformation, is that what you mean?
No, it's not a central extension. It's a deformation. You'll find some products of generators here typically.
It's a W algebra.
You might, well, I don't know. Okay, so so now I say you have a deformation, but the deformation actually doesn't matter. But there's another place where you deform the algebra, and that is in the coproduct. So the coproduct is deformed. Now, what is the coproduct? The coproduct tells you essentially the action on multi-particle states. So the coproduct defines action of the symmetry generators on multi-particle states. So let's consider first a Lie generator. So this generator JA, which sits at level 0 of the loop algebra. And here this multi-particle action is undeformed. That means essentially we still have the SUN that we have exact SUN symmetry in our model at all stages. So the coproduct, this is the coproduct of JA, is defined to be JA cross 1 plus 1 cross JA. So effectively, it tells you the action, gives you the action on two particle states. So It means when you want to act with this symmetry generator on a two-particle state, you should act on the first side and then act on the second side, leave the other side invariant, and then add up the two things. So that's how we define the action on multi-particle states anyway. So here you don't do anything new. In fact, if you want to act on a multi-particle state, you would do this. So this is a multiple co-product, and this would give you, well, something like that. So this, and the only rule you need is essentially that the co-product of 1 equals 1 times 1. So if you apply this co-product to this, say to this first side, then here you split up the generator, and here you just create another one. So it's a short exercise to show that this holds. So in that sense, the co-product defines the action on two-particle states, and if you iterate that, you get the action on multi-particle states. Okay, now let's consider another generator. In fact, if you're interested in a reference on Youngians, there's one introductory paper or lecture by Denis Bernard, and it has Youngians in the title, or Youngian title. Okay, so now we should consider the other levels of the loop algebra. So consider, let's call this YA, just perhaps denoting Youngian generator, and this should be the first level of this loop algebra, or Youngian algebra. And there you define the coproduct as follows. Whoops, this is YA. So you have the same thing as before, just like in a standard tensor product, but here you add a deformation, and you could write it as this. So this is the other deformation in the Youngian, and the one that will be relevant for us. And well, why is this useful?
Is that J naught then? Or J?
Yes, this is J naught. If you want, I can put zeros here.
660 BC?
Yes. Thanks. Right. So in this way, you can set up the first level of the Youngian, and then by commutators of these generators, you can also create the coproduct on higher levels. But why is this useful? Well, before, sort of, you just had the standard tensor product, so all the sides of the spin chain were completely independent. The action didn't didn't see that two sides were neighbors or anything else. Whereas here you see the action sees two sides at the same time by this deformation. And that sort of links up the spin chain in the algebra.
What do you mean two sides? We're talking about general S-matrix.
Well, okay, sides of a spin chain, okay, right, got carried away. So if you talk about some particle model, where these particles have certain flavors, you might as well sort of add. If you take a snapshot of this, then it looks like a state in a spin chain. So okay. So this links up nearest particles which are adjacent or close to another. Yes.
So this F has nothing to do with structure constant.
It is the same. It is the structure constant with one index lowered.
But why you call it deformation? Is there some deformation parameter, or this is just deformation?
You might put an H bar in here, but you can also scale it away. So this thing just gives you sort of a nearest neighbor structure on your particle space. These two particles are nearest neighbors, while these are not, and the Youngian will now really see the order of particles, and that's good. So in our other notation, in our other basis, we could write this as this. I'm doing this because we are needed. So this would be JAC cross JCB minus I over 2 JCB JAC summed over C. So now this coproduct or this symmetry generator is now actually a symmetry of the S-matrix. So so we have that this coproduct commutes with the S-matrix, and also this YAB coproduct commutes with the S-matrix. That is provided if, well, first of all, YAB should act on a state PC like U of P what was it? U of P well, to the first exponent times JAB on C. So this is an evaluation representation. And furthermore, this function f of p must equal minus I u of p for some reason. This function f of p was the one, how did we write we wrote this R matrix as, oh, what was that? 1 plus f of p minus f of q plus 1 f of p minus f of q plus permutation. I think this was the form, and if this function f of p equals iu of p, so if actually here you have f of p, then this R matrix or S of t being the R matrix times the permutation will commute with the Youngian. So this is now really a symmetry of the S matrix, and we get this form for the R matrix, well, just substituting that, putting in a few factors of I gives you u of p1 minus u of p2 plus ip divided by u of p1 minus u of p2 minus I times a phase that we don't know yet. Okay, and then this function defines sort of the model. So the model defines you this function. In different models you could get different functions, but this will always be of the same form. It will always be a difference of these two The R matrix will always be a function of the difference of these two functions.
So in relativistic cases, that's just the rapidity of the particle?
Yes, that's just the rapidity. And for the Heisenberg XXX model, U of P would be given by 1/2 cotangent P over 2, I guess. And in relativistic models, arc
P is m sinh theta.
sinh, yeah.
So your U would be theta, what you would normally do.
Oh yes, right.
P is equal to m sinh theta.
Sort of. And that's for Heisenberg, and this is for relativistic models. Okay, now I wanted to show you how to construct an R matrix or an S matrix from Youngian symmetry. I think this is a quite instructive exercise. So I'm sort of turning this logic around. Let's assume we don't know this form yet, and then we impose this relation to find this form. And the good thing about it is that you'll only encounter linear equations in all of this, so you don't have to have so much imagination. You just plug it in and solve. So by SUN symmetry, that is, if you want this coproduct of JAB, we already know that this R matrix will equal G12 times permutation plus F12 times the identity, whereas where these two functions are not yet determined. And the S matrix is given by this permutation operator times the R matrix. Okay, so to work efficiently, you typically use a test state. A very simple test state would be P1, Q1. So you take two particles of the same flavor but with different momenta, and act with y21 on the state. So if you act with that, you'll see that, well, one of these indices, one of these flavors should be changed to 2. So this 1 goes to 2. Okay, so act with this coproduct. Now, we're going to need this later, so let me do it here. Let's act with this guy on P1, Q1. So this is what you want to use. Okay, so this gives you, first of all, U of P when this guy hits the first side and turns the index to 2. Then you add U of Q when the Y hits the second side. So this is P1, Q2. And then there's the deformation consisting of these two terms. And, well, yeah, there are a couple of terms which simplify in the end to plus I over 2 P2 Q1 minus I over 2, let's see, yeah, P1 Q2. So these two terms come from the deformation. This is just the standard loop algebra, if you like. Okay, now we can write this in a different fashion. Well, using the fact that for SUN, the product of two things, two fundamentals, will be the symmetric plus the antisymmetric part. So let's project this onto symmetric and antisymmetric part, and then we get U of P plus U of Q for the symmetric part, P1. So this is supposed to denote the symmetrization of indices. And the other one will be U of P minus U of Q minus I with these two indices antisymmetrized. So for standard SUN, you know that when you act on a symmetrized product, this will always act map to itself by, let's call this, well, you can't see it. This is J, and the J will map the symmetric to the symmetric and antisymmetric to the antisymmetric. But here you see you start with something symmetric and map it to itself by the Youngian, so you get a symmetrized part. But you also get from here to there with this Youngian generator. So that shows you that these two parts will be related in the bigger symmetry. And if you compare it to loop algebras, well, the only thing that's new is this I that appears here, and well, this is the deformation. And now it doesn't suffice to make these two things equal. You have to make them equal up to a shift of I. So that's that, and we'll come back to it. So then, let's compute the following. So let's compute this commutator on our test state. So you can write this out. First you, there are a couple of terms, let me write them down. So first you act with S12 on this state. So S12 is this guy. This state here is symmetric, so the permutation will do nothing. So you will always get a factor of 1 plus. So you'll always get this factor of G12 1 plus F12, and you get this state back. Well, actually, so this will be G12 1 plus F12. Then the co-product remains acting on the state Q1 P1. This is the permutation operator that exchanges these two. So that's from the one side. The other side, you still have S12 acting on the co-product of this with P1 Q1. This piece you can read off from that board. Okay, so let me. Okay, and then you act on this. So let me just write down the final result. This is that. Well, I should abbreviate U of P1, U of P and U of Q by that. So what remains here is Q1 P1 symmetrized, and then here G121 plus F12 U2 minus U1 plus I. Actually, I should put it like that. So this guy here is just what comes from here. And actually, I think I made a mistake here. Okay, I just flipped those two. So this is this term, but you have to realize that before acting with this, I've exchanged Q and P. So here will be a U1 and there will be a U2. And then you subtract the other thing. This is a plus.
Excuse me, on the term that sorry, on the line above the one that you're writing at the moment, I assume it's an anti-commutator of Q1 P2, not Q1 P1. You know, on that line.
Yes.
Next term to the left. No, keep going. Keep going.
Oh, that
Not
one?
on that. Yeah, it's 1, 2, I think, isn't it?
Oh,
Because you're back to yeah.
yeah, of course. Well, the number of ones and twos is of course, always the same. Okay, so so what do we have? Well, this -1 comes from this. The permutation on the antisymmetric state will give you -1, and well, a couple of other signs. But you'll see that this part already drops out, and you're left with the equality of these two terms. So so what you find is, so also G12 doesn't matter. You get 1 plus F12 U1 minus U2 minus I equals -1 plus F12. And well, I probably should have written it this way. So you get this equation, which, if I didn't do a mistake, leads to F12 equals minus I U1 plus I U2.
Why do you put an I in the original definition? If there's some kind of hermeticity in the top equation of the middle board, why is there an I there particularly? Is there because of some?
Yeah, it's conventional. You don't have to put it. If you don't put it there, you'll get an I-free notation, I guess. There's no I anywhere. But, well, actually, I prefer a half-free notation. But I mean, all these factors of 1/2 anyway.
I thought U1 and U2 were sort of real. But
right. If you want that U1 and U2 are real, like in here, if the momentum is real, then the cotangent is real. So so then you need to have these factors of I to get a Hermitian representation of everything. If you don't, if you you could put a factor of I in front of every U, but then U would be imaginary for real stuff. So, yeah. Anyway, so this is the same we got before. So we say that F12 equals F1 minus F2, so F1 equals minus I u1, or if you want plus a constant, that doesn't really matter. And so in that form, we get, just by solving linear equations and not thinking too much, the R matrix. So this is the R matrix. Okay, now let's briefly discuss this R matrix a bit further. Namely, you have this structure and it has certain poles and it has certain zeros. In particular, you could, so this is about poles, zeros of the R or S matrix, and their relation to bound states. Okay, so you could write this as R12. Now, if you act on a symmetric state, the permutation will be trivial, so all of this boils down to a 1. So this will be R01 times the projector to symmetric combinations plus, if it's an antisymmetric combination, then this will be a minus. So then you get u1 minus u2 minus I u1 minus u2 plus I projector on antisymmetric states. So there are a couple of poles and zeros perhaps in this function which we don't know. So but let's look at this combination. So here you certainly get a pole when u1 minus u2 equals minus I, and you get a 0 when u1 minus u2 equals plus I. So what does, I mean, why do we get these poles? Why couldn't it be just a smooth function everywhere? And that's related to these to this transformation rule under the Youngian. In fact, we should also look at how the Youngian acts on an antisymmetric state. So this is the action of the Youngian on a symmetric state. Let's consider the antisymmetric state. Let's act with this guy on P1 Q2, so some antisymmetric combination. What we'll find is this equals 1/2 well, u of q minus u of p. Now it's plus I times the state P1 Q1. So then we could complete this picture, and let me complete it here. So here we have the symmetric state. Here we have the antisymmetric state. Let this be this yellow be the action of SUN. So these map just to themselves, SUN, and then let red be the action of the Youngian. So red, as we saw, can map from this to this. It can also actually map from here to there. But it can act between the two components in this way. So this gives you the irreducibility of the coproduct. But if you look at the factors, let's look at this factor, then you see that the one line is broken if up minus uq equals I. So up minus Q must not be I. If it's I, then this arrow will be broken, because then the action of the Y will just annihilate the state. So this is plus I. And UP minus UQ equals minus I. So if that equals minus I, then this line will be broken. So that means in the generic case, when these are just any values, then you have completely irreducible modulo, completely irreducible representation. However, at these 2 points, which certainly coincide with these 2 conditions, then this multiplet will split up, and you can find a submultiplet which you can isolate. So let's say if U1 minus U2 equals that, so if you break this line, then you can take this antisymmetric combination, and the Youngian will act only within this submultiplet. So the antisymmetric part will be irreducible, and here the symmetric part will be irreducible. And while these you can then these will then be bound states. But it seems I don't really have the time to go into this subject. But bound states, in some sense, mean well, if you have 2 particles which are linked in that way by this relation, and you scatter them with something else, then the scattering process will not disintegrate this state. So bound states means the scattering is elastic for these guys.
I think what you've shown is that kinematically the formation of a bound state would be allowed. In other words,
Well, I haven't shown this this here, but
yeah, I
yeah,
don't
kinematically the formation of a bound state is allowed, right?
Right, but whether it actually exists in any
Right.
specific model, I think, is a dynamical question. And you
Right.
wouldn't expect
But
it
at
to
least,
be,
I mean, what I want to say is that the scattering would allow a bound state to exist.
right, it wouldn't lead to a contradiction.
Right. So typically, if you have 2 particles and a third one, then this third one goes through it and will somehow mess up at least the 2-particle state. But if you have this, well, yeah, if you satisfy this condition, then this configuration will be sort of stable. And one particularly interesting thing is, if you keep going, you can also construct bound states with multiple constituents. And for instance, you could take a sort of completely antisymmetric combination of n states, and then this would form a singlet of SUN. So in a Young tableau, when you stack the boxes all on top of each other, then you get a singlet of SUN, and this will also be a sort of the baryon. Yeah, for SU3 it would be the standard proton baryon. But okay, so this would be a singlet of SUN, and it would also be. You can also this singlet would also be a singlet of the Youngian. And you might wonder, if you scatter a complete singlet of the full symmetry algebra with anything else, then, well, nothing should happen in some sense. Now, the analogy with baryons is not very good. But okay, at least baryons don't interact strongly, so.
Can you
Well,
deduce, I mean,
Yeah.
in this case, can you deduce a kind of crossing symmetry from the condition that you've just described?
I
Now just
think the
why-
crossing symmetry will always do this.
Right.
So when you compose bound states or possible bound states, and you reach a singlet, then a universal R matrix would act trivially on this singlet. So the scattering for singlets must always be trivial. And so for SUN, you get this condition, which is, well, quite nonlinear, I guess. But the S matrix should be such that the scattering of this bound state is trivial.
Does the algebra imply that this state would also have zero energy? I mean, or
I guess no. Maybe.
yes,
Maybe
yeah,
not.
that's not really.
Okay, I mean, if it doesn't have zero energy, then the Youngian might act on it. I'm not pretty sure. Okay. Okay, I think we've done enough of that, so let's do something something concrete. So all of this was more or less a warm-up for AdS CFT. So now I want to discuss the S matrix of AdS CFT and how you derive it. This will mostly follow along the lines of this article. Well, maybe I should say here that this the poles and the zeros of the S matrix can be related to bound states. So that would be the final conclusion of this exercise. Fine. So let's consider it from the point of view of gauge theory. N equals 4 gauge theory, and this would perhaps also be a good point to start listening again if you have dropped out, because N equals 4 gauge theory seems to play a central role in any of the talks that you hear here, and so you might be familiar again. Okay, so in this gauge theory, you take a scalar which is often called Z. Sometimes you write it as phi 5 plus I phi 6, so two of the scalars in a complex combination with some charge. And let me just briefly run through the coordinate beta ansatz setup. So you introduce a vacuum, a state. It's just a state. I mean, you call it the vacuum. Or more precisely, it's a ferromagnetic vacuum, which is the state where in a spin chain you just take only these scalars, lots of these scalars. Actually take an infinitely long chain, if you like. And this state, as you might have heard, is half BPS or chiral primary, and therefore receives no correction. So for instance, the anomalous dimension will be 0, and there's actually nothing to do for this state. We already know its energy. So it's a good starting point for adventures with other excited states. So let's introduce some Hamiltonian which annihilates the state, which is to say the energy is 0. And this Hamiltonian is mostly d minus j. J is some SO6 charge. This is the scaling dimension. Okay, so we've solved that. Next, we want to flip one spin. So this is called a one Magnon state. And let's call it, well, again, this is the state PA. And we take a plane wave or momentum eigenstate I, P, K, where we flip precisely one of these spins and so take away the scalar field and put this A field inside. A can be one of many flavors. So this is certainly an eigenstate of the Hamiltonian if the only thing that the Hamiltonian can do is shift this state around. So the Hamiltonian is local, and if it shifts this thing only around, then well, Hamiltonian is homogeneous, so momentum eigenstates will be eigenstates of the Hamiltonian. But the question is, which states can the Hamiltonian just shift around, and which states does it break apart? So what are the possible single spin flips? So for that you would look at the combination d0 minus j. This is actually what BMN did in their famous paper. So you look at the combination of d minus j. Let's look at certain states. A scalar phi I, phi j, where j goes from 1 to 4. These states have classical dimension 1, of course. The scalar has dimension 1. The charge, the SO6 charge under which Z is charged, so that thing that rotates the 5-6 plane, certainly these guys are not charged under that. So J is 0, and D0 minus J therefore is 1. So single spin flip means this combination is 1. This is the lowest non-trivial value you can get. I mean, the vacuum has d minus j equals 0. Everything else has more than 0, and 1 is the lowest value for this. And because the Hamiltonian commutes with that, if you have just a charge 1, then this thing can only be shifted around. It can't be changed into something else. Maybe we can see something else later. So this is one possibility, a covariant derivative of of this background scalar is also allowed, where mu goes from 0 to 3. So this combination here has classical dimension 2, one for the derivative and one for the scalar. But now the charge j is 1 because z has charge 1. So this is 1, and here you get d0 minus j equals 1. And there's some of the fermions which also satisfy this bound. So the dimension of a fermion is 3 over 2, and you want those fermions where this charge is 1/2, so d0 minus j is 1. So these are the allowed states, and just by looking at the charges, you can convince yourself that if you put this excitation somewhere in the middle of a chain and act with the Hamiltonian, then the only thing the Hamiltonian can do perhaps is shift this guy around, just by looking at the charges. There's nothing else it could possibly do. These 8 plus 8 combinations are the only things you can do. Well, you have 16 fermions.
Okay, it's half of it.
So there are 8 fermions which have charge minus 1/2. So d0 minus j equals 2. And that means if you put such a fermion into your chain, what can happen is that the Hamiltonian, say, takes these two and makes them something else, namely 2 of these. So the total charge here must, of course, be preserved, but it can turn this into, let's see, perhaps a derivative and well, let's give them a tilde. So these are those guys with tilde. So the Hamiltonian can change this guy into, say, a derivative and one of the other fermions. And therefore, this combination is not stable. When you act with the Hamiltonian on it, it will disintegrate this spin into 2 spin flips, 2 different spin flips. And then you don't really have a single particle, but you have 2 particles only with a given total momentum. And so that's not what you want. In fact, you should view this state here as two different excitations which which are independent, but at some point they cross, and at this point where they cross, you need this spin orientation as a sort of UV regulator or sort of coincident effect.
Can you also have a Z-bar insertion?
Yes. Z-bar, for instance, here you get dimension 1, but j is minus 1. So this combination would be 2. You can think of other things like d mu phi I gives you dimension 2, but charge 0. So in total 2. Or if you like, d mu, d nu, d rho, f kappa lambda. So this would have 1, 2, 3, 4, 5 here, and charge 0. So this is a peculiar thing where you have 5 spin flips which happen to reside at the same site. But it's not really important to to enumerate all states. So in some sense, on an infinite chain, the only degrees of freedom which are close to this vacuum are given by these 16, these 4 plus 4 and 8 fermion magnons. So how much time do I have?
You started a little bit late, so you could go on till about 20 to 25 past.
Mm-hmm.
Another 10 to 15 minutes.
Okay. So are there any questions regarding this?
I mean, what is the relevant supergroup for which these 4 plus 4 things form a sort of representation? I mean, what subgroup of
I'm coming to that.
Right.
And this will actually be essential to the construction. So if you understand the representation and the symmetry, then you're almost there. You just have to do a few calculations. So that's that, and then you would want to look at something like multi-particle states, PA, QB, ... which you would write as, well, these are asymptotic states. So you would want to look at states where this spin flip is very far apart from the other spin flip. So you have the sum over k much less than L, e to the I p k plus I q L, where you have this spin flip A at position k and B at position L. And you know that in the planar limit, everything will act locally on this chain. So because these spin flips are considered to be very far apart, they will never interact. I mean, everything that acts will see only these things individually. And all the UV physics will be captured by the S-matrix. Okay, so I should go into group theory. And the group theory for n equals 4 is PSU 2,2/4. And, well, thinking about conformal symmetry alone is already a pain in the neck, and then you want to mate that with supersymmetry, and it might be a very complicated group, but it's not quite so. So PSU 2,2/4 is a group. It has 30 plus 32 generators, and you should, roughly speaking, think of a matrix, 8 by a matrix, which you split into well, graded matrix. So you split it into 2, 4, and 2 rows and columns. And in these boxes, you write the various components. So this is more or less a matrix algebra. And in here, you find an SU2. Here, you find an SU2. Here, you find P, the momentum generator. Here, the conformal boost. So this block, which I split up here, is the conformal symmetry, and this is the group SU, the bosonic group SU2,2. But it's convenient to split it up in this fashion and separate this part from that part. Now, not too hard to imagine what fits here. This is the SU4 or SO6, if you like. And then there are the super symmetry generators. This should be Q. This should be S. This should be Q bar. And this should be S bar. Or maybe not. I think you flip these two. I get confused with that. Okay. So that is how this superconformal algebra splits into the internal symmetry, the Lorentz symmetry. Well, Lorentz symmetry. Where's that? Some combination of that. Okay. Anyway, this is the conformal symmetry Right.
SU2 is a Lorentz problem? Euclidean
P
Lorentz. SU2 cross SU2 is SO.
yeah, it's certainly Euclidean Lorentz. Well, also get confused about that. And I guess for string theory, it's not too hard to imagine how these things act. This will act on the sphere. This will act, these outer box will act on the AdS part. Now, we want to look at the residual algebra. That's the part that that annihilates our vacuum and also preserves the Magnon number. The Magnon number being the classical dimension minus charge. Okay, so how does that work? In this matrix picture, you would draw it like as follows. So I have to split this matrix like this. And then this part here, this is a, okay, what's this? This is a 4 by 4 block. And these guys are Magnon creation operators. So when you act with any of these here, you will create a Magnon from the vacuum. For instance, you act with a momentum generator, which is like adding a derivative. So if you add a derivative on this vacuum state, you'll put a d mu z somewhere. So you change the number of magnons. So this part here will certainly create magnons, and these others will too. These guys are Magnon annihilation operators, and so these are certainly also 4 by 4. And what remains is the residual algebra, and that is more or less PSU2/2 here and PSU2/2 there. You see this block is split into half. These are bosons, these are fermions, so this is PSU2/2.
Slightly confused. The Magnon annihilation operators, yet they don't annihilate the vacuum.
They annihilate the vacuum, yes.
Dude, I thought somehow that only the PSU2/2
Well,
squared annihilates the vacuum. That's why you were picking that out.
no, okay, these guys annihilate the vacuum, but of course, if there's no Magnon and you would take it away, you have to annihilate the state.
So that corner also annihilates the vacuum.
Yes.
Right.
I mean, that's why I say it preserves the Magnon number. So in some sense, you want emission operators that annihilate the vacuum, whereas these would be the conjugates of those. And well, so this is already very suggestive how you would put these these 4 plus 4/8 magnons, how you would, how they transform under the residual symmetry. Well, I mean, these are the Magnon creation operators, so it essentially tells you that the 16 magnons should organize in a 4 by 4 matrix, which here transforms, I mean, the columns transform under PSU2/2 and the rows under this PSU2/2. So that tells you about the Magnon representation. So you have this 2x2 4x4 matrix, and here you, for instance, take put the 4 scalars, and here are the 8 fermions, and these would be d mu, the 4 covariant derivatives, which sort of transform under a bifundamental of this this algebra. Okay, and essentially it tells you that, well, if you scatter, then somehow, well, in this integrable system, everything is sort of determined by the symmetry. So in that sense, the rows will scatter independently of the columns, and therefore the S-matrix of AdS, or the worldsheet S-matrix of AdS CFT, would be given by an S-matrix for PSU2/2 times an S-matrix of PSU2/2 prime. Let me put a prime here. And if you like, there's also an overall phase factor, which you can't, I mean, as always, you cannot determine from algebra. So so certainly this simplifies the matter dramatically, because you now don't have to consider scattering of 16 times 16 in states. So you write this down. Before you have this big AdS CFT S-matrix, where you have 16 possible in states at both of the legs. So 16 times 16 and 16 times 16 out states. So this would be 16 to the 4, which is 6, 5, 5, 3. 6 elements that you would have to determine. But instead, you need to consider only sort of this. This setup where you still have 16 times 16, but these split up into 4 times 4 and 4 times 4, 4 times 4, and then recombine. So you have to consider only an S-matrix of 4 to the 4, which is 256 elements. And I guess in the last lecture I want to construct this S-matrix from the symmetries. And yeah, thank you.
Questions?
Can we first check the loop algebra for specific model and n equals for superamplitude any construct?
Yes. But maybe we should first construct the Lie algebra, and then you can put on top this Youngian algebra. Yes, you can do it. And it is a symmetry of the S-matrix. But it's not constraining in this case.